So we're trying to generalize the concept of a free particle of mass m. That's where this Klein-Gordon scalar field comes from. And if we go back to non-relativistic quantum theory, this looked like, so at let's say t equals 0, we have a free particle located at x equals x naught. Let's say this is a one-dimensional universe. What we found was that the wave function psi of x at t equals 0 looks like it's a delta function, right? So it's some constant times x minus x naught. And we then looked at the weights, right? Which k values are associated with this particle that's perfectly localized in space. And by the uncertainty principle, this object has to have a large range, in fact, infinite range in momentum or in k value. So if you go back to the lectures, we had something like this. Well, this is how we get the phi of k's, right? We put in the psi of x is 0, which is this object. And we have e to the minus ikx, and we're integrating in x. And this gives us e to the minus I k x naught. So, psi of x is, we're thinking of it as some normalization constant, and we're integrating the plane waves with weighted values of momentum, or k. In dk, we could turn this into a dp integral if we wanted. So this becomes a over 2 pi square root, integrating, let's make k not go to infinity here, but we get e to the minus I k x naught, e to the I k x in dk. And if, well, let's just rewrite this as, maybe we'll derive, we want to derive, we want to see that this is a delta function. It's sort of an alternative way of writing the delta function. So we have e to the I, because we'll see these kinds of things in quantum field theory as well, this kind of a thing, right? We know that this psi of x is, in fact, this, because this is where we started. So we can do this integral, right? And we get, as we did in the quantum course, constant, not very interesting, I x minus x naught, e to the I k x minus x naught from minus k naught to k naught. And this gives us, right, this is cosine k x minus x naught plus I sine k x minus x naught minus the same thing. So we get rid of the cosine. We have twice I times the sine, it's some overall constant. We don't really care, right? That's just a constant. But the sine survives. The I will go away. So we have sine of k naught, x minus x naught, over x minus x naught. And right in the limit, as k naught goes to infinity, right, this is always something that's between 0 and 1. So what does this function look like? As we saw, right, as we approach x naught, then the function goes to infinity because we're divided by 0. So the limit as we're doing that is kind of like that. And we can sort of see that this is a representation of the delta function, right? So this is also a delta function. So let's make a comparison with what we've done in quantum field theory. We called the solution to this disturbance at one location, which is sort of the equivalent of it's the analog of what we just looked at now, a free particle in a non-relativistic limit at one location at t equals 0. At t equals 0, we create a disturbance. We called it phi 1. Let's just call it psi 1 to make the parallel with this, psi 1 of x. And what we found is that we have to do this integral. Let's write it maybe. And then we have e to the minus ik x minus x naught. So it's sort of a similar kind of thing. It's same kinds of ideas. It's really plane waves, except that the restriction on k is greater. So the weights of k are more restricted because they have to reflect. Unlike the free particle in the non-relativistic limit, there was no limit on what k could be. In this case, k is related to m by the specific dispersion relation of the Klein-Gordon equation, right? The relativistic energy condition.